Okay, so this is the first installment of some advanced technician training on SAE J1939 and controller area networks. This isn't geared towards any one particular manufacturer. It's applicable to any product, any machine which makes use of SAE J1939 to communicate between the controllers on the machine. What I have here is a program called Circuit Lab, which is a circuit analysis program. I'm going to use it to demonstrate what happens with the electronics or at the electronic level with, in this case, a CAN transceiver. CAN transceiver is the device. It's a generic device. This particular one, this TJA 1050, is used quite frequently within the automotive industry. So it's one that I can pull up the data sheet for. You can pull this up from the internet for pretty much any place that sells these components. Put this number in and you will be able to pull down a data sheet from a variety of manufacturers. So in this data sheet, it provides a lot of technical information. This is designed for electronics engineers, for hardware engineers, to determine what temperature they have to watch out for devices, what they have to maintain within. It provides a lot of technical information, probably much more than you'd probably care to see, but some of the important stuff we can pull off of it are basically this block diagram of how this transceiver works. So this is the device which is within the controller. It's contained inside of a typical controller, such as this generic electronic control unit that I have here. This could be an engine controller, this could be transmission, this could be a body controller, whatever it is. It would have contained in it one or more of these CAN transceivers. They may be from a variety of manufacturers, different part numbers from this one, but this is one which, as I indicated, is used quite frequently within the industry. So I've taken basically this block diagram. I've taken pieces of it here. And what I'm going to do is kind of go through and discuss the input stage of it first. We'll talk about the input and then what happens as we transmit, as we look at more of the components that are contained within it. So I care about right now, I have something called VCC, which is specified in this as being approximately 5 volts. So I have to have this supply voltage for this at approximately 5 volts. The controller outside of this, contained within the control unit, would have a 5-volt supply. I'm just showing it contained here as this 5-volt supply. So there's my 5-volt supply. We have these devices which are either some sort of FET, a MOSFET, and you can just think of those as being switches. So these are either on or off. They're either going to permit this 5 volts to go through and then to allow this line to pull to ground, or they're going to be open. So you could think of them as switches, and that's exactly what I've done in this model. I've replaced those with switches because everybody understands how a switch works compared to a MOSFET. So those, you can imagine this is like a finger that's flipping the switches, and it switches both of these at the same time. So it's either provided with the 5 volts and ground, or it's not. Also contained within this is something that indicates 0.5 VCC, so that means 0.5 times VCC, or 2.5 volts. So half of VCC is what we care about here, and we're going to hold this at 2.5. This 2.5 may sound familiar because you've probably measured this voltage on the CAN bus numerous times with your meter. So here's the 2.5 volts that you're actually measuring that's on the CAN bus. This is where that comes from. And I only have one controller that I've modeled here. If we had others, they would be out sitting parallel on the CAN bus. So if we look at this, I've simplified the circuit that I have on my screen. This circuit I have basically modeled, or I put over here. So we have the CAN high line and the CAN low line. I've taken both terminators on the machine, the 120s, put those in parallel, and you end up with 60 ohms, right? You've measured that before. So all I care about, I don't need to separate these out. I'm going to keep this as simple as I can. So we can take something that's really complicated like this CAN transceiver and the whole CAN network, and we can start off and just break this down into small pieces. If we break this down into small pieces, it makes it a lot easier to understand. As I indicated, I can run a simulation with this. I'll go ahead and run first a DC simulation. So I show both of my switches open. What's it going to look like right now from this DC perspective, and nothing real exciting. CAN high over here is shown as 2.5 volts. CAN low is also shown as 2.5 volts. So this indicates one logic state, and we would refer to this logic state when the bus is at both lines at 2.5 volts approximately as being the recessive state. We care about in CAN, we care about the voltage difference between CAN high and CAN low. So CAN high minus CAN low, and in this case we have a value of 0 for that. But if I look at this switch, if I say, and I can do some analysis here, if I decide that I want to say at some period of time, I'm going to have this switch and this switch both closed, what will that look like? And to do that, I need to basically look at this in what we call the time domain. So this is more like an oscilloscope view of what's going to happen. So I'm going to start at 0 seconds. At 1 millisecond, I'm going to stop. And at 1 microsecond, I'm going to do this 1 millionth of a second. Every one of these, I'm going to sample this circuit, kind of like a scope, at 1 millionth of a second. I've got the switch designed so that it is going to close, or it's going to change state at 100 microseconds or 100 millionths of a second. So it's going to start off with the switches being open, and then once we reach 100 milliseconds or microseconds, both of these switches are going to switch. If I look at this one, it should be set at the same thing because we want both of these to change at the same time, right? If we go back and look at this driver, the output of this driver, never would I drive this one on and not drive this one on. That's bad. We don't want that. We will drive both of these on at exactly the same time. It's going to be given a signal when it's ready to transmit to push this on. So we'll go through a lot more of that. I just want to give a brief introduction. We'll do another video that it talks about transmission and what happens when we transmit versus when we receive. And let's go ahead and run the time domain sweep then. So the time domain, you can see here, I'm going to go ahead and take this one off first. What we have is, as I indicated, we have 2.5, both are held at 2.5, and once we reach 100 microseconds. Once we've hit this period of time, I said both switches switch, and I'm going to leave both of those switches on for that period of time. We end up with CAN high having a voltage value, if you see on the screen there, 3.58, approximately 3.6. CAN low is approximately 1.4 volts. This is with respect to ground. If I go ahead and put the brown one on here, let's take these off. We look at it. What happens is the difference in voltage, so it's 0 volts or it's approximately 2.1 volts. And if I go back to my data sheet, okay, so looking at the data sheet, what I care about now, I said the dominant bit. So this is V out. This is while the device, the CAN transceiver, is actually transmitting. So when it's in this recessive state, it's one where it's listening, or that it's broadcasting what we would refer to as a logic 1. We'll talk about a lot of that stuff later on. It's kind of confusing. So, but anyways, when we've got both of the switches on, we are in the dominant state, and so we're broadcasting basically a logic 0, even though it's a differential voltage that is about 2.2 volts. It's considered a logic 0. So the specification sheet indicates that CAN high, for this particular chip, it can be, when we're in the dominant state and it's broadcasting, transmitting, 4.25 to 3. The nominal, this typical, is somewhere around 3.6, which is exactly what we saw that I have set this one up for. Same thing for the output dominant on CAN low. That means it's going to pull down as low as 0.5 volts. The nominal, the typical, is 1.4 volts, which is where I set this one to, and the highest that it would permit that to go to would be 1.75 volts. So this kind of tells you that even though this device is within specification, it could have a range of anywhere between 3 and 4.25 when it's driving the bus on CAN high to the dominant bit. Same thing for CAN low. It can be anywhere between 0.5 to 1.75. What that means is I could go from machine to machine, and if I'm looking for this CAN high on an oscilloscope to be exactly 3.6, It might be, it might not be. And as we'll go through some of the failure modes, looking at the grounds that are on the various controllers, we could see that we could really have some variation in this. So getting too hung up on CAN voltages, getting too hung up on what you see for some level can lead you down basically to trap, and you'll spend a lot of time looking for something that isn't really a problem. As I said, CAN is concerned really with this differential voltage. Same thing. So to be guaranteed to be a dominant, to be dominant state, to be a dominant bit, we need the voltage differential, the CAN high minus CAN low, to be somewhere as low as 1.5, nominal typical 2.25, high 3. So if we see anything in this range, this chip should indicate that that is a dominant bit that it's seeing, whether either it's transmitting that or it's receiving it. Okay. Okay, we'll go back to the simulation behind this. So this is probably enough for right now. We'll make these short, do a few of them. This is kind of in review. What we have here is we're modeling, or we're showing what the CAN transceiver looks like in a typical controller that would be on a machine which uses J1939, which uses CAN. We'll go through next time, or at some point we'll add other components, and we'll talk more about this dominant state and recessive state, because this is crucial to understand, I guess, to the fundamentals of CAN, to not get so hung up on what you see for an exact voltage, and especially if you're going to use an oscilloscope or something, that we need to keep in mind that we're looking for this differential, or this difference in voltage. And we'll go through a lot more of that as we progress and as we add more of the components that go into the transceiver.